All right, so this video is going to be on solubility tests. So, bad start, y'all. Rewind. Okay, so we will be using this as one of our first steps to help identify unknown organic compounds. And so, essentially, what you're going to do is you're going to have a test tube, and you're going to have an unknown sample, right? This unknown sample could be a liquid, it could be a solid. Um, and you're going to test that liquid or solid in a variety of solvents, okay? So you're going to test it in water. You're going to test it in 5% sodium hydroxide or sodium bicarbonate or HCl or concentrated sulfuric acid, okay? So the first step, easiest thing, we're not wasting chemicals, is hit a little bit of that unknown with some water. Okay, so you're gonna have, let's just see some gorgeous blue water here. We got about 2 mils in a test tube, right? And let's say we have a poopy brown solid. Okay, so you want to just put a tiny bit of that poopy brown solid, or 1 drop of that poopy brown liquid, right, into that 2 mils of water. Now, observe, see what happens, right? Once you can determine that it is soluble or insoluble, then you kind of you follow the chart, right? So here's the thing. You want to make sure that you add a very, very small amount initially, because everything has a maximum level of solubility in water, right? So let's say you added a little bit too much and only some of it dissolved, but you couldn't really tell because you added so much. So if you add a little bit at a time, you can more easily identify whether or not that solid or liquid is soluble, right? Obviously, the liquid, we want to talk about miscibility or immiscibility, but in the end, it's dissolving in the water if it's miscible, right? So if you don't see 2 layers, then it's miscible. You want to be careful. You can also look for mixing lines when you're doing the liquid. That's helpful. But then you also want to be careful with the solid. If you have large chunks, you're going to want to grind that, right? So if it's large, like crystals or chunks, then hit that with the mortar and pestle. Mortar and pestle. That's going to be your friend. So it's going to make fine particles. It'll more easily dissolve because you're going to decrease the surface area, right? So once it dissolves, what you want to do is add a little bit more, okay? So this is going to help you identify approximately how soluble. Is it like mildly soluble or like super soluble, okay? Because that's going to help identify perhaps what type of functional groups you have. Is it a super polar compound, or is it not polar at all, or mildly polar? This is very helpful information. This is ultimately the goal that we're trying to gather. Okay, so let me get rid of all of these. Oh no, I did the 5%. I don't want to get rid of the 5%, y'all. Just the red. Okay, so let's say it is soluble, right? So we're gonna follow that doot 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 doot. Then we're gonna go doot 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 doot. Okay, so now what we're gonna do is we're gonna hit this test tube with a little bit of litmus paper, right? So we want to see if it is acidic, basic, or neutral, okay? It also is helpful if you have enough of that material mixed in the liquid to actually contribute a decent amount of base or acid or nothing to give you a more easily identifiable like reading. So you don't have to use necessarily the red litmus or blue litmus, or you could use the universal litmus paper where it's going to change a variety of colors, and it'll have like if it's like red, it's acidic, or if it's green or yellow or whatever, blue, it's different pH levels. It gives you more specific pH readings. But essentially, you use the pH of that solution to help you identify what it is. So it could be a low molecular weight amine or carboxylic acid or a neutral compound. So the neutral compound, you want to bring your eyes down here. That could be any of these boxed compounds. So the alkenes, alkynes, alcohols, ketones, aldehydes, nitro compounds, esters, ethers, and amides. Okay, so we also have inert compounds down there that are alkanes, alkyl halides, aromatic compounds. Okay, so but basically that's the low molecular weight. Remember when we're talking about solubility of organic compounds, we in lecture we discuss the number of carbons and the number of polar functional groups that can hydrogen bond, right? So it's usually 5 or less for every one polar functional group that can hydrogen bond will give you some solubility in water, okay? And so that's why the low molecular weight comes into play, okay? But that's it for the solubility in water. Let's say it was not soluble in water, though. Let's say we had to go this route because it was insoluble. Well, now we have to create a brand new solution. And so this was H2O in that tube. But for this one right here, we have to set up a brand new test tube. We're going to put 2 mils of sodium hydroxide. And this is 5%, okay? Just like stated here. Whoa, simmer down, Jess. Okay, and then you kind of just do the same thing, right? Like, is it soluble? Then if it's soluble, then you go this route. If it's insoluble, then you go this route. Okay, so on and so forth. So let's say it is soluble. If it's soluble, then you want to use a 5% solution of sodium bicarbonate. And then if it's soluble, then you go up this route. And then that helps you identify that it is a strong acid. It's got it's a carboxylic acid or maybe a phenol of some type. But if it's insoluble, then you come down here and it's a weak acid. It's generally a phenol. Okay. So this is a pretty cool chart that we've borrowed from, what is this, Pavia. It's like an organic laboratory techniques book, 4th edition. Shout out to Pavia et al. But let's see. Let's say it's insoluble. Oh, I deleted the 5%. We want to hit that with 5% HCl. Excuse me. I feel like I sneeze all the time during videos. My bad. Okay, so once you hit it with HCl, if it's soluble, then you're going up here. It's a base. It's an amine. Boom. If it's insoluble, then you want to, got to create another tube. Okay, hit it with some concentrated sulfuric acid, which is also labeled 18 molar sulfuric acid. A little fun fact for you if you want. If it's soluble, then it's going to be one of these types of compounds, and if it's insoluble, then it's likely an inert compound. Okay. So, here we go. What the heck? Why is it? I already told you why it would be like a low molecular weight amine or carboxylic acid or neutral compound, right? Because they all have polar functional groups, right? Especially the amine and the carboxylic acid, and then the neutral compounds that could have like an alcohol or ketone or aldehyde, right? So those are polar functionalities, and that means they're gonna be mildly polar if they're low molecular weight. So that's why they'd be soluble in water. Okay. So why would something be soluble in sodium hydroxide as well as sodium bicarbonate? Well, it's a strong acid. So this is a strong base, right? And this is a weaker base. So that's why if it's a strong acid, of course it's going to get deprotonated by the strong base. Since it's a strong acid, it's also going to be deprotonated by that weak base. And so carboxylic acids and some phenols, that's going to take care of those groups. So what's going on with this some phenols thing, right? Some phenols would be like if you had, so a phenol, remember, is this. And a phenol, let's see, let me just copy this one because we got to put that down here anyway. What's going on, bro? What's going on? Why are you tripping? Oh, man. Pissed. Okay. Put it right there. That's a phenol right there. That's what happens below. Okay, so some phenols means that if you have a phenol with what we call electron withdrawing groups on that benzene ring. So like let's say it had a nitro group here, here, and here, right? Those NO2s are actually withdrawing electron density, which helps stabilize the conjugate base of this particular phenol. And so that's actually way more acidic than a regular phenol. And so since it's way more acidic, it is a strong acid, and it's going to be deprotonated by this weak sauce sodium bicarbonate, okay? So that's what it means by some phenols. It's going to have some like electron withdrawing group that's going to help increase the acidity of that OH, okay? If it's insoluble, that's because it's a weak, sodium bicarbonate is a weak base, and we have a weaker acid. So a phenol is a good example of that, okay? Let's say I'm going to get rid of these now. Deleted. Okay. Still want to put that 5% there though, sorry. Let's say when we hit it with sodium hydroxide, it was insoluble. What? Why are you insoluble, bro? Well, now what we want to do is hit it with the 5% HCl, okay? So if it is soluble, why is it soluble? I'm going to need a little bit more room. Let's say we had, I don't know, let's just do this. Let's say we had NH2, and then that, I'm going to draw it as HCl like this. Boom, 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 and H3 would form with a Cl minus. So this is an ammonium cation. We know that salts, this cation with this anion, are super soluble in water, right? And so that's why it would immediately be soluble if you hit that with HCl, because it's an amine and it's a base. It's going to deprotonate it's going to grab that proton, and it's going to become a salt, essentially, and an ammonium cation, and be very soluble in the water, which is the rest of that that solution, right? It's 95% water, 5% HCl. Okay, so mostly water. Now, if it's not soluble in the HCl, then what we want to do is hit it with concentrated sulfuric acid. Okay, so what's the deal with this? Why does this help us identify the compounds? So the easiest example that we would be aware of right now is alcohols, right? So essentially the sulfuric acid is going to react with alcohol. So let's say we had, let's just say we had this, right? So, or no, I don't like that one. I don't like that one because I don't want to think right now. So I'm just going to do this. So let's say we have this compound right here. It's got 1, 2, 3, 4, 5, 6. Let's just do this. 7, 8. It's got 8 carbons on it. It's definitely not going to be a low molecular weight, anything with that's soluble in water, right? It's beyond the 5 carbons for one hydrogen bonding functional group. And let's say we hit it with sulfuric acid. Why is it going to dissolve? Well, remember, sulfuric acid is a very strong acid. It's a source of a proton. It's going to grab that proton, and then we've got 2, 4, 6, 8. It's going to become this here, right? But that's a secondary carbocation, right? So first of all, that's a cation, right? So that's already going to be soluble. But then that can even leave and then you can form an actual cation. And then HSO4 minus is going to be floating around. So essentially, you create something that's charged by the addition of that sulfuric acid, and therefore you are going to create something that is soluble in that sulfuric acid. Okay, because remember, this is concentrated sulfuric acid, so there's sulfuric acid all over the place, right? Aldehydes, ketones, these other functional groups, they are also going to be reacting with the sulfuric acid. So if we have a carbonyl group, so this could be a ketone or an aldehyde, right? It's going to get the H plus, and then it's going to be that oxonium ion. That oxonium ion's charged, and so it's going to be, and it's also going to be soluble in the sulfuric acid. Okay. Now one of the other things on there was like an alkene, and we know that alkenes in the presence of acid will also. Well, we probably don't know that yet. Sorry, but they react also. Okay, so let's just say that we've got hydrogen on there, and then we've got the positive charge with the he gone, HSO4 minus, right? So again, we create a charged intermediate, something that's positive and something that's negative. It's going to be soluble in the sulfuric acid. Okay, so if it's not soluble, then it's an inert compound, and it's an alkane, an alkyl halide, an aromatic compound. What that means is it's inert compound, meaning it doesn't react, and so it's not going to react. Nothing's going to change, and it's not going to become a charged compound. It's not going to be soluble in sulfuric acid. And so essentially, that's how you're going to use sulfuric acid to help identify a neutral or inert compound. Okay, so it's pretty straightforward, honestly. I think the bulk of the information is like down here, like what's going on, why do these help us identify the functional groups. And so I hope that was made clear. If you have any questions, of course, you can reach out to me. But just take detailed notes, and then when the time comes, you'll be good to go to perform these, and you're going to be pros.